In this video, I will show you how to estimate the bearing capacity using finite element method. In this video, I'm using RS2 software from Rock Science package. I also estimate the bearing capacity using analytical solution with using these equations: Q equal to 2 plus pi times C. This soil that I have here is cohesive soil, so there is zero friction angle, and the cohesion is 0.1 megapascal. Okay, so the dashed green line represent the analytical solution from this equation, and the red line represent the solution from finite element using RS2 software. This is the input, this is the geometry of the model, this is the stages. So what the idea of this is a step stages approach. So we're gonna increase the loading step by step until we get the curve yielded, and at yielding point we call that the bearing capacity. So as you can see, both solution or both approach almost have the same answer. So as you can see, the displacement will increase as we increase the loading in the RS2 until its yield. So that yield point would correspond to the bearing capacity. So this is the stage. We're going to assign 17 different stage with loading factor, as you can see on the screen. The field stress we're going to assign constant, the units metric, NPA, and the analysis type is plane strain. Okay, and this is the stages, and this is the load, which is basically comes from multiply the load, which is in this case 0.01, very small, by the load factor that we're going to assign into RS2. So that's the green dashed line. As I said, it's from the analytical solution, and the red is from the finite element. So let's go to RS2 model. So first of all, we're gonna go to the settings and then stages, and we're gonna assign 17 stages here. Okay, and then let's create our geometry first. Actually, let's click on this icon here and type T here and then enter. So let's copy paste the geometry from our Excel file to here. This is our geometry. Type C to close. So now we have assigned the geometry. Now actually let's assign the loading. So first, before we assign the load, let's make sure the field stress it's constant. The default is gravity, but I'm not going to assign any gravity, and I'm just going to give it select field stress type constant, and then I'm going to go to distributed load, uniform load, and value is 0.01 megapascal. Okay, and then I'm gonna click on stages. Before that, let's create angle from horizontal. It's gonna be -90, and stage factor, load factor, it's gonna be 1, 5, 10, 15, 20, 25, 30, 35, 40, 42, 44, 46, 48, 50, 51, 52, and 53. So this factor will be multiply of the magnitude of loading at each stage. Okay, click OK here, click OK, and let's assign it here and here. So you can see now we have 17 stages. As we go further, the load is increasing because it will be multiplied by the factor that we assigned already. Okay, so we define the load, we define the geometry. Now let's define the boundary conditions. Actually, let's create the mesh first. I haven't created the mesh, so click on mesh, discrete. I'm gonna make it 8 noded quad. 200 looks fine. You don't have too many layers, so that's fine for now. Mesh. So this is how it looks like if we change this to 4. I just want to show you how it looks like. As you can see, we don't have any surface photography except one single layer here. So with this case, it will be fine if we can make it finer. That's fine too. I think that's too much. Let's make it 250. Okay. So in case you don't have the boundary condition, you can assign them from here. So I assigned here a ruler, and I assigned here fixed on this side and the bottom also fixed. This model actually is axisymmetric. So what does it mean? So in the ruler, we will allow the vertical deformation, but we're not allowing any horizontal deformation. Here, both x and y fixed, and also on this side, both sides are fixed. Because it's axisymmetric, that's why I'm assigning ruler on this side. So it's going to be mirrored to the left side. Okay, so this foundation actually width is 3 meters, and it's 3 meters also on the other side. So total is 6 meters. It's like a strip footing. Okay, let's check the units. We have the right units in BA, as I mentioned in the beginning of the video. So now we assign the geometry, we assign the mesh, we assign the boundary condition, we assign the load. Let's check for the field stresses should be constant, and it should be plane strain. Yep. So now we are ready to solve our model. Click on solve here to solve. It should take a few seconds to finish the progress, the analysis. So now it's analyzing stress strain for the model. It's almost done. Yeah, it should take a few seconds to complete the analysis. You can increase or decrease the time of analysis if you go to the settings and reduce a little bit the tolerance. Instead of 0.001, you can make it 0.01 just to reduce the time of analysis. Also, if you make the mesh coarser, of course, you will also reduce the time of analysis, and you can save some time. But if you have thin soil layers, you need to be very careful, and you need to optimize the mesh to cover all the soil stratigraphy that you have inside your model. Just wait a few seconds. It's almost done, 88% complete. 2 more stages to finish. One more stage. So this approach, the step loading approach for calculating the bearing capacity, you can use this approach in finite element or finite difference, it doesn't matter. It should follow the same approach. So now we finished the analysis. Let's click on interpret to see the results, and I will show you how to get the deformation or the results to create that red plot that you saw in the beginning of the video. So now we have the deformations, okay, for each stage, you see. So how I did that, actually, I clicked on here and I went all the way to displacement, and I clicked on total displacement, okay. Now I'm showing the total displacement, and then I clicked on this icon here, label contours, and then I clicked here. Now I can see the deformations, okay, for each stage. Actually, I didn't show you how to define the material property. So if you want to define the material property, you can go to the property, define material, because I already did that. So you can assign the unit weight of the material, the porosity, the stiffness in terms of Poisson ratio and Young modulus, and then the strength in terms, I used here more column model. So as I said, it's cohesive material. So the friction angle here is 0. And I only assigned, actually you don't need to assign the tensile strength. You can just use the cohesion only, 0.1. Okay, you can assign this as 0. But I didn't show that because I already defined the material property. So let's close that and go back here. And from each stage, I'm showing the deformation. So what you need to do is go back here, and then you have the stages, you have the load from all the stages, and then you need to assign the deformation, the displacement, and in the middle of the foundation, and just plot the load on the y-axis and the displacement on the x-axis to plot this red line. Once you do that, you will see the curve is yielding. At that yield point, you can consider this as a bearing capacity. So the bearing capacity is about 0.5 to 0.51. So I got it 0.51 in the analytical solution, and the finite element solution, it's also almost the same results. So that's it for this video. So I just want to show that another feature in RS2. For example, if you want to see the deformed mesh in this model, you can click here. This is exaggerated. You can change the exaggeration if you click on this icon, I believe. Not this icon. Yes, this icon here. Not this one. Sorry about that. 1 second. Yes, you can. Yeah, you can change it from here. You can see the exaggeration of the deformed mesh. And you can see also the vector, also the deformed color map. You can see it here. You can see the external or the existing ground only, the external boundary deformed from here. And for example, if you have at this region, you have some sensitive soil layers or some sensitive information, and you want to make the mesh more fine, you can just go here and click on increase mesh element here, for example, and the software will automatically make the mesh finer wherever you want. For example, if you have many different thin layers here, you can make the mesh finer wherever you want in the model and make everywhere coarser. You can go again here, mesh, mapping mesh, or sorry. Yes, you can increase the mesh wherever you want, and also you can check the quality of your mesh by going to mesh quality and show mesh quality. Since we have only one material, the quality is 100%. There is no any bad elements or anything like that, so we can check the quality from here. But this is very easy model, so I just want to give you an example of how to calculate the bearing capacity. I hope you like this video, and thank you so much for watching. Bye.